Okay, so this is a great demonstration of the fact that angular momentum is a strictly conserved quantity. So if you have an isolated system, so no angular momentum coming in, no angular momentum going out, no external torques acting on the parts of that system, then the total angular momentum contained in that system remains constant. You know, for sure, you could have angular momentum in one part of a system change, but then there will be a corresponding counter change in another part of the system in such a way that the total angular momentum remains constant. So we'll for sure be talking about stuff like that, but more importantly and more interestingly, we'll be talking about exactly the mechanism whereby angular momentum is transferred from one part of a system to another part of a system, such that the total angular momentum remains constant. Okay, and that transfer mechanism is of course a torque acting over time. Like transferring linear momentum is a force acting over time, transfer of angular momentum is a torque acting over time. So that's the really interesting thing to try to get out of this demonstration and to figure out, okay? Okay, so what are the parts of our isolated system? Well, there's three parts. The first part is this awesome bicycle wheel. Okay, so clearly I can store angular momentum in this rotating wheel. So I curl my fingers in the direction of the rotation, which is like this, and then my thumb points in the direction of the angular momentum stored in this wheel. Okay, so now I can change the direction of that angular momentum just by grabbing onto this axle and just forcing it to just point in different directions. Okay, so what I notice when I force it to point in different directions, it has no effect on the angular speed of the wheel, which means that the magnitude of the angular momentum stored in the wheel doesn't change. It's just ICM times the angular speed. Okay, but what I can change is the direction of the angular momentum stored in this wheel. Okay, so right now I have, say, 1 unit of angular momentum in the vertical upwards direction. I grab onto the axle and I force it to point that way. Now I have 1 unit of angular momentum in that direction, to the left, horizontal to the left. I can force it around like this. Now I have 1 unit of angular momentum horizontal to the right. Okay, and I force it all the way around like this. Now I have 1 unit of angular momentum vertical down. Okay, so the magnitude of the angular momentum stored in the wheel doesn't change, but I can certainly change the direction by forcing it to go whatever direction I want. Okay, but what I notice when I'm forcing it to point in different directions is that this object, this rotating object, does not behave like a non-rotating object. When this object is not rotating, is not storing angular momentum, you know, I can do this, no big deal. It just feels like any other kind of object. But when I give this object angular momentum, it's a very different story. Okay, so when I try to change the direction in which the axle points from that to that, okay, so I go like that, I exert like a twisting force, a torque that way, okay, then the wheel responds in this really weird way. Okay, so it's just amazing. So I strongly encourage you to buy one of these bicycle wheels and try it out. Okay, so when I try to do this, when I try to rotate about this axis, then the wheel responds by trying to rotate about the other axis, a perpendicular axis. Okay, and so it just feels really weird. Okay, but it feels weird only because we don't have a lot of experience with handling objects that store a lot of angular momentum. Okay, we're used to objects that don't have any angular momentum, like pushing around shopping carts and stuff like that, right? But handling objects that have angular momentum, we're not so used to that, right? And so at first it feels weird. But the purpose of this demo is to try to explain clearly why this spinning wheel is reacting that way and how that sort of weird behavior is not weird at all. First of all, it's perfectly understandable in terms of simple Newtonian physics, and secondly, it plays a crucial role, that precise behavior plays a crucial role in how angular momentum is transferred between parts of a system in such a way that the total angular momentum remains constant, angular momentum conservation. So the second part of our isolated system is me. And I'm sitting on this chair, which can rotate freely about a vertical axis. Okay, so I've got some moment of inertia about this vertical axis, and I've got some angular velocity about this vertical axis. So right now I'm storing angular momentum in the vertical up direction. Okay, I can also store angular momentum in the vertical down direction. Okay, but I cannot store angular momentum in a horizontal direction. To store angular momentum in a horizontal direction means that I would have to be rotating like this way. Okay, so that's not happening. Okay, so I can only store angular momentum in a vertical up or a vertical down direction, no horizontal angular momentum. And moreover, and this is really important, because this chair is free to spin frictionlessly on a vertical axis, means that I cannot, me and the wheel can never exert a torque, a vertical torque on the earth. Okay, so just look at this. I've got this chair, it's frictionless. To exert a vertical torque on the earth, okay, I would do this, but it's completely frictionless. If I take the chair off and do this, sure, now I'm exerting a vertical torque on the earth. But because it's frictionless, I can't exert a vertical up torque on the earth, transferring vertical momentum down into the earth, nor can I exert a vertical down torque on the earth, transferring the vertical down angular momentum to the earth. Okay, so as far as so me and the wheel, I'll be doing stuff with the wheel. Me and the wheel are completely isolated from the earth as far as transfer of vertical components of angular momentum are concerned. However, there's no trouble in transferring horizontal components of angular momentum between me and the wheel and the earth. Okay, so as I mentioned, that wheel, when I'm doing this to that spinning wheel, it does sort of like weird reaction sort of effects. And those weird reaction sort of effects are precisely the things which exert say a horizontal torque on me, horizontal left torque on me, which can be transmitted to the earth and thus transfer horizontal left angular momentum to the earth, or vice versa. Okay, we'll get to that. So the third part of our isolated system, of course, is the earth. Okay, so now I understand that the earth is rotating and so on, and storing angular momentum already and all that, but you can just completely ignore that. Okay, so for the purposes of clarity in your own mind, you can just imagine that the earth is this gigantic ball of rock. It's floating out in the middle of empty space, floating out in the middle of nowhere, and it is at rest in an inertial reference frame, and it is not rotating, okay, at least to begin with. Okay, it's storing no angular momentum to begin with. Now, of course, we're going to do stuff. We're going to give angular momentum to the wheel, and we're going to be like rotating and this and that. And sure, angular momentum in a horizontal direction is going to be transferred to the earth and then back and this and that. Okay, but when we start the experiment, we will just imagine that the earth is at rest in an inertial reference frame and not rotating, storing no angular momentum. Okay? All right, having said all that, let's now do the demo. Okay, so now I've stored, say, 1 unit magnitude of angular momentum in this spinning wheel, and I've directed the axle so that that angular momentum is up. So now we have 1 unit of vertical up angular momentum stored in the wheel, 0 angular momentum stored in me, and, well, there might be some angular momentum stored in the earth, but who cares? All we care about is changes to the angular momentum stored in the earth. So we might as well assume that the earth is right now storing 0 angular momentum. So the total angular momentum in the system is 0 plus 0 plus 1 unit of vertical up angular momentum. Okay? So let me just spin that up again. It slows down a little bit. Okay, so 1 unit of vertical up angular momentum in our system total. And what I'm going to do is I'm going to grab the axle and I'm going to force it into a horizontal position. So now the wheel is storing 1 unit of angular momentum horizontal to my left. So my left is now this way, then it's this way, then it's this way, then it's this way, and so on. Okay? The point is that the angular momentum stored in the wheel is horizontal. Okay? How can that be? Because there is no horizontal angular momentum in the system. Okay? So it must be that when the wheel is like this, and it's storing 1 unit of horizontal left angular momentum, then the earth must be storing 1 unit of horizontal right angular momentum, so that the total horizontal angular momentum in the system is equal to 0. Okay? Now what about the vertical angular momentum? Okay, so we started with 1 unit of vertical up angular momentum stored in the wheel, and that's it. Okay, then I force the axle into a horizontal position, and you'll notice that I start rotating counterclockwise. Okay, so I start rotating vertical up. Okay, so I am storing angular momentum in the vertical up direction. Well, how much? Well, it should be exactly 1 unit of vertical up angular momentum stored in me. And that's because, as we talked about, as we discussed, there's no way that me and the wheel can transfer any vertical component of angular momentum to the Earth. So the vertical amount of angular momentum that the wheel started with can only come to me and can't go to the Earth. So I must have, by conservation of angular momentum, 1 unit of angular momentum in the vertical up direction. Okay, and so I'm spinning slower than the wheel, for sure. But that's just because I have a greater moment of inertia than the wheel. So my greater moment of inertia times my slower angular velocity is equal to the wheel's smaller moment of inertia times its greater angular velocity. The angular momentum, the magnitude of angular momentum stored, is exactly the same. Okay? So now we'll do that same experiment, but we'll turn the wheel completely upside down. Okay, so right now, 1 unit of vertical up angular momentum stored in our system. Now the wheel and the Earth have opposing horizontal angular momentum. I have 1 unit of vertical up angular momentum. If I turn the wheel completely upside down, you'll notice that my angular velocity goes up. In fact, it exactly doubles. Okay, if I go back, now it's the original angular velocity, and then, let myself come around, and then back to 0 angular velocity. Okay, so let me spin this thing up again. Okay, so 1 unit of vertical up angular momentum in the wheel. Okay, some horizontal angular momentum in the wheel canceled by the horizontal angular momentum in the Earth. 1 unit of vertical up angular momentum in me. And if I go all the way over, then I have 2 units of up angular momentum, vertical up angular momentum stored in me. And why is that? Well, because the wheel now has 1 unit of vertical angular momentum down. And so I need to have 2 units of vertical angular momentum up. So the total vertical angular momentum in the system is 1 unit of vertical angular momentum up. Okay? Okay, so far, all we've really said is that, so if the angular momentum in one part of the system, say, increases along some axis, then the angular momentum in some other part of the system must increase along the same axis in the opposite direction by the same amount, so that the total angular momentum remains constant. Okay, but so what? We haven't really talked about the really interesting part, which is, well, how is angular momentum transferred from one part to another? Okay, and that's by torques acting over time. Okay, so that's the really interesting part to understand. Now it turns out understanding that involves this idea that when the wheel is spinning and I try to rotate the axle, the wheel reacts in really weird ways. It's that reaction which is precisely responsible for the correct transfer of angular momentum between parts of the system so that the total angular momentum remains constant. And it's not a weird thing, it's not a complicated thing, it's actually a super dead simple thing. All it is the idea of inertia, the idea that an object in motion would like to continue that same motion unless forced to do differently. Okay, that's all it is. Okay, so we're not used to thinking of that in the context of objects in rotational motion and so on, but now we'll see. It's actually really quite simple. Okay, so and as physics majors, this is the kind of understanding that you should be getting with this kind of stuff. Okay, you should understand this stuff. It shouldn't seem weird and mysterious. It should seem beautiful and completely comprehensible. Okay, so let's see. It's just simple Newtonian physics. Okay, so what we've got is this wheel rotating like this. Okay, and so what we said is, yep, I forced the axle into a horizontal position, so now the wheel has horizontal angular momentum to the left, to the left, to the left. Okay, so right now the wheel has horizontal angular momentum to the left. Well, there is no total horizontal, there is no angular momentum in the horizontal direction. So it must be, by conservation of angular momentum, that the Earth has somehow mysteriously gained angular momentum, horizontal angular momentum to the right. But how? Okay, so this is the interesting part. Okay, so the how is very simple. So let's imagine, so we're going to start with the wheel spinning like this, okay, and we're going to imagine what happens when we exert a twisting force on this axle and twist it just through a small angle, like 10 degrees or something like that. Okay, so what's actually happening? Well, let's start with the axle vertical like this. Okay, and so we're going to focus on 2 points of the wheel, the point over here and the point over here. So when the wheel is spinning, at one instant of time, that chunk of mass is moving exactly horizontal forward. Okay, and it would like to continue to move exactly horizontally in the forward direction, unless acted upon by other forces. Well, there are other forces. There are radial forces that the rim of the wheel exerts on that chunk of mass so that it doesn't continue to move like that, but it actually moves around in uniform circular motion. Okay? Great. So now what we're going to do is we're going to say we're going to tilt, while this wheel is rotating, we're going to tilt the axis a little bit to the left like that. Tilt it like that. So what happens over at that point right there? Well, you can see that that point gets a component, a small component of velocity in the vertical direction. So it's spinning fast like this. It has a large component of exactly horizontal forward velocity, but when I go like this, then I give it a little bit of velocity in the vertical direction. So the velocity it has at this point is not exactly horizontal forward, it's tilted up a little bit. So what it would really like to do is continue to move exactly like that, a little bit up. Okay? But there's this radial inward force, this centripetal force, which is going to curve its motion. So what it ends up wanting to do is, when I tilt the wheel a little bit like that, what it would want to do is continue to go like this, up, and then rotate around, and then come down. Okay, let's apply the same analysis to this chunk of mass. Okay, so this chunk of mass, at this instant of time right now, is moving exactly horizontally backwards. Okay? When I go like this, what I do is I add a small downwards component to the velocity, so that chunk of mass is actually moving exactly horizontally backwards with a small component, with a small tilt down. Okay, and so what it would like to do is it would like to continue to just go down like that. Okay, and yet there's this radial force inwards making it move in a circle. So it moves in a circle but downwards. So it wants to come down like this, rotate around, and then come back up. Okay, and so what the wheel wants to do, so when I exert a twisting force or a torque on this axle in this direction, what the wheel wants to do is do that. Okay, this side goes up, this side goes down. It wants to do that. So the torque that I'm exerting is about this axis towards me, horizontal towards me, and yet what the wheel wants to do is that. It wants to do that. Because it wants to rotate about a perpendicular axis. I exert a torque this way, along this axis. It wants to rotate along a perpendicular axis. That's what gives that sort of weird feeling when this wheel is spinning fast and you try to change the direction of the axis. Whoa, it feels weird. I go like this, and I go like this, but what it wants to do is this. Okay? I go like this, what it wants to do is this. All right? So, but meanie that I am, I'm preventing it from doing what it wants to do. Okay, so it wants to do this. Okay? But I'm but I'm preventing it. I'm actually forcing the axle to move just like that, not back like that, just like that. Okay, and so because it wants to do this, it exerts a force on my upper hand back towards me and on my lower hand towards you. Okay, and so it exerts a force on my hands this way, but I'm not allowing my hands to move. I'm keeping them rigid like this. And so what it is there's a force on my upper hand this way and a force on my lower hand this way. Well, that's a torque. Okay, and so the wheel is applying a torque to me. In what direction? Well, in that direction. Okay, and so it's exerting a torque in the horizontal right direction on me. And so if I could absorb angular momentum in the horizontal direction, then my angular momentum horizontal to the right would increase. But I can't absorb horizontal momentum, but the Earth can. Okay, and I'm not isolated. Me and the wheel are not isolated from the Earth as far as transfers of horizontal angular momentum are concerned. All that's happening is, I'm here like this, and if you were to come and exert a twisting force on my hand like this, you're really through the axle of this chair that's connected to the floor, you would be exerting a twisting force on the Earth this way. And so you would be transferring angular momentum to the Earth in that direction. Well, that's exactly what we want, right? Because here's the wheel, like this, and when I when I force this axle to rotate this way, I'm forcing the angular momentum of the wheel to change from vertical up to tilted a bit over. So the change in going from this vector to that vector is a vector that's exactly in the horizontal left direction. Okay? And so, so the wheel gains some horizontal left angular momentum. Okay? By the mechanism that we just discussed, the wheel reacts this way and exerts a horizontal right torque on me and through the axle of the chair to the earth, and transfers, by that torque acting over time, transfers horizontal right angular momentum to the earth in exactly the amount to cancel the horizontal left angular momentum gained by the wheel. So that by the time it comes all the way around like this, it's got one full unit of angular momentum horizontal left. While the Earth, in that process, in that time, that torque acting over time, has transferred one full unit of angular momentum to the right, to the Earth. Okay, so it's really cool. So it's absolutely true that it feels weird, and yet it makes perfect sense, and it explains exactly how it is angular momentum can be transferred to the Earth to compensate for the horizontal angular momentum that the wheel now has, so that the total horizontal angular momentum in the system always remains zero. Okay, it's really cool. Okay, so we talked about how a horizontal component of angular momentum can be transferred to the Earth, and the rate at which that's happening is maximum when we are doing the rotation near the axle being vertical. Now we're going to talk about how it is that vertical angular momentum is transferred from the wheel into me, because that certainly happens. There's vertical angular momentum in the wheel now and none in me. Okay, when I do this, there's no vertical component of angular momentum in the wheel, and it's all come to me. Okay, and the rate at which that happens is maximum when the axle is nearly horizontal. So we'll analyze the situation when the axle is nearly horizontal. So we're going to go from this position here, say, to this position here, okay, with the wheel spinning. Okay, so when the wheel, or let's say just from horizontal to a little bit down like this, okay? So when the wheel is spinning horizontally like this, when I force the axle to tilt like this, to rotate like this, then additional vertical angular momentum is transferred to me. Okay? So how does that happen? Exactly the same mechanism. It's just simple inertia. Okay, so when the wheel is in this position like this, let's focus on that chunk of mass and that chunk of mass. So at this instant of time, this chunk of mass right here is moving exactly horizontally towards you. And it would like to continue to move exactly horizontally towards you, unless acted upon by other forces, and those are the forces, the centripetal forces causing that chunk of mass to not move like that, but move around in uniform circular motion. Okay, but now what I'm going to do is I'm going to rotate the wheel. I'm going to rotate the axle like this. Okay, and so look at what happens to that top chunk of mass. Oh, look, it gains a component of velocity in that direction. Okay, so it's happy to be moving exactly horizontally towards you. I do this to it, it gets a small component of velocity in that direction. So now its velocity is really that way. Okay, and so what I'd like to continue to do is exactly move horizontally in that direction, together with but then it's forced to, because of the radial forces, to basically move in circular motion, but there's still that component of velocity that way. So what it wants to do is move outwards like this, okay, and then it'll come back like this. Okay, so outwards like this, and then come back. So maximum outwards over here, outwards like this, and then come back. Similarly for the chunk of mass down here. This chunk of mass is moving, at this instant of time, is moving exactly horizontally and backwards. When I do that, I give it a component of velocity in that direction. So then, instead of wanting to move exactly horizontally back, it'll want to move exactly in this a little bit in this direction. Okay, and so as it comes around, as it rolls around here, it wants to come out like this and then go back. Okay, so this chunk of wheel wants to go out like this and come back. this chunk of wheel wants to go out like this and come back. So what the wheel wants to do is lat, okay? So the wheel is spinning like this, and when I tilt it from here to here, when I tilt the axle from here to here, what the wheel wants to do instead is to go like that. So I exert a torque about this axis. What the wheel wants to do is that. It wants to rotate about that axis. Torque about this axis. Yeah, torque about this axis. It wants to rotate this way, about a perpendicular axis. Again, that's what gives it that weird sort of feeling when you handle a rotating object. It's just like super weird, okay? And yet it's precisely that weirdness. It's just associated with simple inertia, and it's precisely that weirdness which exerts a torque. Because the wheel, so I go like this to the wheel, I go like this to the wheel, okay, and I go like that. What it wants to do is that, okay, but I prevent it from doing that. Okay, I just hold it like this. I force the axle to rotate like this. I don't let it do this, but it really wants to do this, okay, and so what it does is it exerts a force on my hand this way, on my right hand towards you, and on my left hand away from you. It exerts a force on my hands, like it exerts a torque on my hands. It does this to me, but I'm holding them rigid, and so really what it does is it exerts a twisting force on me. And so it's exerting a torque in this direction, in the vertical upward direction. It's twisting me like this by my hands, through my hands. Okay, and so it's transferring that torque in that direction, acting over the time that I'm doing this, is transferring vertical upwards angular momentum to me. And so my angular velocity, my angular momentum in the vertical direction increases. Okay, so, and the rate at which it's increasing is maximum when we're just coming through the horizontal position. So you can see that. Okay, so right now, I'm going to be rotating this, I'm going to be forcing the axle to tilt, to rotate around. Okay, so there's very little angular momentum that I have. Look how slowly I'm increasing in angular momentum. Okay, but as the axle nears the horizontal position, the rate at which I'm gaining vertical angular momentum is greatest. Okay, and then when I come all the way around, now I've got twice the, now I've got 2 units of vertical angular momentum up. Okay, and the maximum rate of transfer happened right through this point over here, right through when the axle was nearly horizontal. Okay, so that's why we analyzed it at that point. Okay, so isn't that amazing? So these rotating objects like this, they're just remarkable to handle and remarkable to feel the counter reaction when you exert a torque. Okay, it wants to rotate about a perpendicular axis, and it just feels so weird, but it's not weird. It's super simple. It's just inertia. And that effect is precisely what's responsible for the proper transfer of angular momentum between parts of a system so that the total angular momentum remains constant of an isolated system. Yeah? Okay, so now we come to what is perhaps the most interesting aspect of this demo. Okay, so let me just remind you about something that we've already talked about. Okay, so I force the axle into a horizontal position, and the wheel gets a horizontal angular momentum to the left, to the left, to the left, to the left. And of course the Earth gets a corresponding angular momentum to the right, to the right, to the right, like this. So there's no horizontal angular momentum in the system. But the point is that the angular momentum of that wheel is constantly changing. At one time it's this direction, then it's this direction, then it's this direction. The change in going from that vector to that vector is a vector that's exactly horizontally back. Okay? So in order to cause that change in angular momentum exactly horizontally back, we need a torque that's exerted on the wheel exactly horizontally back. Where could that torque come from? Well, I'll give you a clue here. Okay? So so it turns out I don't need to hold on to this axle with both hands. Huh. That's pretty weird. Okay. So this is an amazing phenomenon called precession. Okay, and it has nothing to do with me sitting in this chair or not. It's a completely general phenomenon. So I'm gonna attach a string to this into this little hole over here and show you how that works. Okay. Okay, so let's talk about this beautiful phenomenon called precession. So just a little historical note here. So dating back to the Babylonians and the ancient Greeks, Hipparchus and so on, there arose this mystery of the precession of the equinoxes. Okay, so it has to do with the spin axis of the Earth precessing around. So now the Earth's spin axis points to a star called Polaris. We call that the North Star. But over a 26,000 year period, the spin axis of the Earth spins around like this, rotates around like this, precesses. Okay, and so after 13,000 years, half that time, the Earth's spin axis will point to a completely different star in the sky. Okay, so anyways, this is you should look this up if you don't know this. This precession of the equinoxes, hugely important mystery, for a long time. And then, but anyways, the point is that that Newton solved that mystery. Okay, and so one of his he wrote the Principia, and he talked about this in there. And so Airy was one of his contemporary scientists, big guy, important guy. He's famous for Airy discs in optical phenomena and so on. Anyways, so he read the Principia, and smart guy, and he said, out of all of the Principia was like a tour de force. It was like incredible. It just changed the landscape. Okay, but of all the mysteries that were solved with Newton's Principia, perhaps the one that delighted the readers the most was Newton's solution to the mystery of the precession of the equinoxes. Anyways, so as physics majors, you should know this kind of stuff. But anyways, let's talk about precession. Okay, because it's directly related to what I was just talking about, precession of the equinoxes. Okay, so the idea is something like this. Okay, so I've got this wheel and it's not rotating, and I'm supporting it from 2 points. One is a rope on the left and the other is my finger on the right. Okay, so if I were to release my finger, the obvious thing happens. Okay, now let's give this wheel a spin. Okay, let's give it some angular momentum, and we'll try the same thing. We're starting off with exactly the same situation. Both ends of the axle are supported. Okay, so I release my finger and it does this. Okay, it does not fall down. Okay, so that seems a little weird. It seems counterintuitive. Okay, I'm going to get back to that. All right, but this is called precession. So why does it happen? Okay, why is it doing that? Well, so first of all, when the wheel is spinning like this, okay, the wheel has an angular momentum horizontal to the right. Okay, and then as it precesses around, that angular momentum changes from horizontal to the right that way, horizontal to the right that way, horizontal to the right that way, and so on. So the angular momentum changes from that direction to that direction. The change in that angular momentum vector from that to that is that way, exactly horizontally towards you. Okay, so that's the change in the angular momentum when the wheel precesses from here to here. Okay, so but what causes changes in angular momentum is a torque. Okay, so there has to be a torque in that direction, causing that change in the angular momentum. Well, where does that torque come from? Well, as soon as I release my hand like this, then there are only two forces acting, and those two forces are gravity pulling straight down at the center of mass, exerting a force of magnitude mg down to the center of mass, and my hand and the tension in the rope, through the tension of the rope, exerting a force of exactly mg up on the left-hand side. Okay, so when the wheel is precessing around, there are exactly two forces acting. So gravity pulling down at the center of mass, and the rope pulling up with exactly the same force at the end. And so the net force acting on this wheel is 0, okay, in the vertical direction. Okay, so there's no acceleration in the vertical direction. So net force is 0, but net torque is not 0. Okay, so as it's precessing around, if we were to calculate, say, the torque about this point, which would be a natural point to choose, okay, then the tension in the rope exerts a force exactly at that point, and so no torque about that pivot point. However, the force of gravity pointing straight down, applied right at the center of mass of the wheel, is located a moment arm distance radially outwards. And so the torque that it exerts is this R cross that F. R cross F is that way. Okay? And that's exactly the direction in which the angular momentum of the wheel changes. Okay? So I'll just show you again. Okay, so I release. Right now there are two forces acting, a downward force of gravity and an upward force of tension, and they add to zero. However, although the net force adds to zero, there's a net torque. And that net torque about the point of the string there is an R cross F. R cross gravitational force is a torque in that direction, and that's the direction of change in the angular momentum. So that torque continuously changes the angular momentum in that direction and makes the wheel process around like this. Okay, so that's great. Okay, so that's the standard first year physics textbook explanation of precession. And there's nothing wrong with the explanation, except that it's incomplete. Okay, and that incompleteness is very important because the explanation completely violates your intuition, right? And as physicists, we absolutely rely on our intuition to understand things, to make progress, all kinds of stuff. So it's very important that you develop a good intuition about how nature works. Now, you might have wrong intuitions, you can correct those, that's fine, but you're always, as physicists, relying on your intuition, okay? So when an explanation completely violates your intuition, you should question it, right? So how does the standard first year textbook explanation of precession violate your intuition? Well, your intuition is this, okay? So when I'm supporting it with both the rope and my finger, and I let go of my finger, my intuition is the tip of the axle is going to fall down, okay? And the fact of the matter is, it does, okay? So when this wheel is rotating like this, and I let go of my finger like this, it actually does fall down a little bit. You see that? Now, let's talk about that a little bit. So why is that happening? Because this is now an explanation that completely agrees with your intuition, all right? So, so let's see. See if I can explain this. It's a little bit subtle. Okay, so the wheel is spinning, okay, and when you release the end of it, okay, so the wheel is spinning and so it has an angular momentum in that direction, exactly horizontal. When you release the end, when you release your finger, you expect the tip of the axle to drop like this, and it does, okay? The problem with it dropping is the following, okay, so angular momentum starts out in an exactly horizontal direction. If the tip of the axle drops, then the angular momentum changes to tilting down a bit. The difference between exactly horizontal and tilting down a bit is a change in the angular momentum vector in the exactly downwards direction. Any change in angular momentum requires a corresponding torque. Okay, and so in order for this to happen, it requires a torque in the downwards direction, which means a torque this way. Well, there is no torque acting on the wheel in that downwards direction. The only torque acting on the wheel is, as we talked about, there's an R cross F gravity. R cross F gravity is exactly horizontal towards you. Okay, there's nothing down about it. Okay, so it starts to drop down like this. Okay, and then says, uh-oh, we're just about to violate the laws of physics. Okay, and so then instead what it does is it starts in that downward direction, but it immediately, like it's like, you know, it's like a curve that starts in the downwards direction, but then immediately starts curving like this, okay? So it curves, drops down, and curves like this. So now the tip of this axle has a component of velocity in that direction, which means that the wheel is doing this. It is precessing. It has started precessing. When you first release it, there's no precession, right? You release it, and the tip drops down like this. It says, uh-oh, we're violating the laws of physics, so let's start moving over like that. Okay, so when it moves over like that, it starts precessing. The effect of that is it's really doing now, it's doing this now. Okay, so now you have a mass, the mass of the wheel concentrated, say, at the center of mass point, which is rotating around. It's like a rigid body fixed at this point with a massless rigid rod connected to a mass going around. Well, that rigid body that's processing around like that has an angular momentum in that direction, up. Okay, so it starts off, the tip of the axle starts dropping like this, we're violating the laws of physics, then it starts moving over sideways. And when it moves over sideways like this, well, now it has picked up an angular momentum component in the upwards direction, which exactly cancels the offending downward tilt. Okay, and then so what it does is it nutates. Okay, so it drops down like this, and then comes up a bit, and it drops down, comes up, and like it's like this. And then there's frictional torque in the pivot point over here, and very quickly it settles down to the motion of the tip settles down to being lower, a little bit lower, but moving exactly horizontally like this. Okay, so now the total angular momentum is you have this horizontal. You initially have a perfectly horizontal angular momentum. It's tilted down a bit. There's an offending downward component to the angular momentum. Oh, but wait a minute, because of the precession, that compensates and gives an upward component of momentum so that the angular momentum is actually perfectly horizontal. Even though it's tilted down like this and precessing around like this, the total angular momentum is exactly perfectly horizontal. And then that perfectly horizontal angular momentum is experiencing it's changing in the perfectly horizontal direction because there's a perfectly horizontal torque coming from the gravitational force acting on the center of mass of the wheel. Okay, so let's just watch that again. So I want you to watch for it dropping down. Okay, because that actually agrees with your intuition. All right, so watch it drop down a bit. See? The axle is not perfectly horizontal. The axis is tilted down a little bit. So that downward momentum has an offending, so that tilt down gives the momentum, the angular momentum of the wheel, an offending downward component, which is compensated for by the precession of the wheel itself, which has an upward component of angular momentum. So that actually the total angular momentum of the wheel is exactly horizontal because it started out exactly horizontal. And there's no vertical component of torque on this thing, so it has to stay exactly horizontal. Okay, isn't that cool? So anyways, this stuff is, angular momentum and torques and all that stuff, and gyroscopes, and they're just full of beautiful, fascinating physics. So, I understand that this stuff is a little bit new, and, you have to, master the cross product and this and that. You have to think in 3 dimensions and everything, but it's super worth the effort. Okay, so just spend the time, master the cross product, really think you really try to think more deeply about angular momentum. It's a truly fascinating topic.